Alright everyone, this is Mr. Bishop. This is my first try at this. Hopefully it goes well. So these are going to be our physics notes for the classroom. So we're going to go through some slides here and just follow along and answer any questions in your notebooks and take notes as we go along. Alright, so to start, our first unit is forces and motion, and here we're going to have some guiding questions over here. So these are our guiding questions. How can Newton's laws be used to explain how and why things move? And how can mathematical models of Newton's laws be used to test and improve engineering design? So these are our guiding questions throughout Unit 1. So anytime we may be confused, try to relate the information back to the answers to these questions. Alright, so first let's get into vector and scalar quantities. This might be a review for some of you, but let's just go through them. So, frame of reference. Frame of reference means that motion is relative. It depends upon where it is observed and measured from. So, for example, standing on a street. You are standing on a street and the bus drives by you. The people on the bus are moving at the same speed as you, but they appear motionless. To the people on the bus, you and the telephone booth, as pictured here below, those appear to be, the telephone booth appears to be moving towards the people on the bus, and then away as the bus drives by you. So, if you think about this, you can recognize that motion is really dependent upon your frame of reference, where you're positioned in perspective to someone or somebody or something else. So right now I'd like you to pause the video for a moment, and we'll be doing these pauses throughout the video. So you'll notice that the notes are in the Cornell note format, so this should be on the left side of your notebook. And I'd like you to think of another situation in which the motion of an object depends upon the perspective of the observer. So like our bus situation, think of something else and write it on the right side of your notebook, and I'll give you a few moments for that. Okay, so frame of reference. Now let's talk about what a scalar quantity. A scalar quantity is a quantity that is described by the magnitude, which is the size or value of it only. For example, these are some examples of scalar quantities. An orange weighs, say, half a pound. This gallon of milk has a volume of 1 gallon. Those are both scalar quantities. They tell us the size of both of these objects, either by weight or by volume in this instance, but they do not tell us anything else, and we'll get to that something else when we talk about vector quantities. So before we go there, again, we're going to pause for a minute, and I want you to draw your own examples. Draw your own examples over to the right of what would constitute a scalar quantity. All right, and now a vector quantity. A vector quantity is a quantity that requires both magnitude and direction. The key word being there, and. So a vector quantity is both magnitude and a direction. For example, an example of a vector quantity is that this car here, pictured, drives 65 miles per hour, that is our magnitude, and it drives 65 miles per hour north on the Interstate 5. So that makes it both magnitude and direction. This is an example of a velocity, which is a vector quantity that has both magnitude and direction. So once again, think of some examples of a vector quantity on your own and record those in your notebook off to the right side page. And we'll pause here for a moment. All right, so vector and scalar quantities. Our first vector or scalar quantity we're going to talk about is speed. Speed is a measure of how fast something is moving. And so that is our definition right there, is how fast something moves is its speed. And so here we have this sprinter. Sprinter runs 28 miles per hour. So now's a good time to ask yourself, is this a vector quantity or a scalar quantity? Same thing with this jet. This jet flies at 1,119 miles per hour. Again, is this a vector or a scalar quantity? So now more on speed. Speed, to calculate speed, and we will often calculate speed in physics. To calculate speed, we use the following formula. We use the formula of speed is equal to distance over time, or shortened S for speed, is equal to d for distance or displacement over t, which is our time variable. And you can use this formula to calculate speed, distance, or time by manipulating the variables. And we'll talk about dimensional analysis in a bit. But say you are walking at 2 meters per second. How far would you walk in 12 seconds? So go ahead and use this formula to calculate how far you would walk in 12 seconds at 2 meters per second. And I'll give you a pause for that. All right, now velocity. Vector and scalar quantities continued. Velocity is an object's speed given in a given direction. So this should clue you into whether this is a vector or a scalar quantity, because, and we'll talk about, and this is a key question, what's the difference between speed and velocity? These are two common terms in physics that many people mistakenly use synonymously with one another, but there is a key difference between speed and velocity. What is that difference? And I'll pause for a moment, and you can answer that to the right in your notebook. All right, so continuing with our example, this rocket down here, is launched upward at 28,968 kilometers per hour. So this is an example of a velocity because we are given both the magnitude, that is that value, 28,968 kilometers, and we are given the direction, of this rocket, which is upward. We're launching the rocket upward, which if we go back and think about frame of reference, that's really in our frame of reference from a human being. Let me draw a tiny little human being. So if there's a human being standing here observing this rocket being launched up, it's really up to him or her because he's positioned on Earth. Now, say that at the same time we were flying in a plane. Let me try to draw a plane. So say someone is flying in a plane. Now, if someone flying in a plane is flying by and sees this rocket being launched, it might not appear upward to the individual in that plane, depending upon where the plane is positioned relative to the rocket launch. It may appear to be at an angle to the plane, so it might not appear to be directly upward. So the plane, the individuals in the plane, the pilot, the passengers, whoever's on the plane, the rocket's going to appear to move a little bit differently relative to the plane compared to this individual back on the surface of the Earth. And then to expand it even further, say there are space or astronauts in the International Space Station. Excuse my poor drawing of the International Space Station, but there's a reason I'm a physics teacher. But say this is the International Space Station, and this astronaut is in a position relative to Earth where he can observe, or her can observe, this rocket being launched. That rocket might appear to be coming directly at the International Space Station. So this should give you a better picture of how frame of reference works, and also that depending upon where you're measuring this velocity from, you could use a different direction than upward. Upward is dependent upon being on Earth, whereas if you're in a plane or in outer space, you might use a different directional description to describe the velocity of this rocket. All right, velocity continued. So how do we calculate velocity? So our equation to calculate velocity is similar to that of speed. You'll notice that very quickly, that our velocity value here is equal to distance over time. So it's almost the exact same equation as speed, except, and it's a key difference, except if we look at these two arrows, and it's typically written in this convention when we write out this equation, that we give directional arrows to our displacement and our velocity, because it tells us that the distance moved and the velocity are both in a certain direction, and that makes it a vector quantity. So remember, when we are calculating velocity, say if we're combining velocities, we need to consider the direction of those two velocities when calculating that velocity. And before we do some practice problems on velocities. Let's discuss our directional conventions. So this is the axes convention. So we consider in our space, we consider direction in 3 dimensions. So when examining movements in space. So we have, and you might recall this from geometry or algebra, but we have our x-axis, we have our y-axis, and we have our z-axis. So I've drawn the axes over here, and it may look a little bit different than you're typical to, you are accustomed to, rather. You might be accustomed to an axis that looks something like this, and this is our y positive, and this is our x positive, and this is our y negative, and this is our x negative. And that's totally fine. When we're only considering movement in 2 directions, this would be our proper axes. So that is 2-directional movement. But as we know in nature, we live in 3 dimensions. And so when we consider movement in space, we need to consider a 3rd-dimensional axis. So we kind of, this is, a flat plane. Or that's not quite right. This is, so here, a flat plane. And then this axis, the z-axis, gives it some depth, and it becomes 3-dimensional. And that is our z-axis. So if we, let me erase this so you can see. So when we label these axes, we usually, what we do is conventional naming of axis. So when we're moving in this direction, that is the y positive axis. If we're moving to the right, that is the x positive. If we're moving downwards, that's the y negative. If we're moving to the left, that's the x negative. And then when our z axis, very similar, so if we're going upwards on our z-axis, that's positive z, and if we're going downwards, that's negative z. So it's important to consider these axes and directions when we're working out velocity problems, and we will be working out a few of those in physics. So here is our question for velocity. The speedometer of a car, moving northward reads 60 kilometers per hour. It passes a car that is traveling southward at 60 kilometers per hour. Now here is a question. Do both of these cars have the same speed? That's one question. And the second question is, do they have the same velocity? So go ahead and answer that question to the right, please. All right, and now we will talk about acceleration. So velocity and acceleration. Another common misconception is that velocity and acceleration are the same quantities, but acceleration is in fact the rate forgot my little separator here. Acceleration is the rate at which velocity changes. It's a measure of the change in velocity. So to calculate acceleration, we use the following equation. This is our equation for the calculation of acceleration. So acceleration is equal to the change of velocity over a time interval. Let's talk about this equation, since it might be confusing in word format, but if we give it some variables, again, we go over here and we see that acceleration has a direction to it as well. So acceleration is also a vector quantity. And to calculate that acceleration is equal to what we call v1 minus v0 all over delta t. So our v0 down here is representative of the initial velocity. So that is the velocity with which something starts with. And then v1 represents the velocity after some period of time. And then our delta t variable, our delta t variable down here is representative of the change in time. So delta is a Greek letter that we use to represent a change in time. That indicates that there has been some time passed from when we had our initial velocity to our final or velocity after that period of time. Sometimes this equation, this is called the final velocity. So, I may have already answered this, but here is the question for you if you missed it. Is acceleration a vector or a scalar quantity?